Good afternoon, everyone. This is Mark Gastongay again with our MI210 lecture. Today, Chapter 4 begins with covariate model building. This is one of the most interesting topics in all of population PK modeling. In fact, from an estimation and inference point of view, it's really what it's all about. So we're going to start today with an overview, talking about the objectives of covariate model development, but then get right into some of the practical pieces, including the common covariate model parameterizations, talk about something called the data reduction step, and then the methods of building covariate models, and there were various methods that I'll review with you today. Finally, ending up with a discussion about making inferences about covariate effects, and then aligning the covariate modeling methods with the objective of the analysis. We've discussed this earlier in the course, but the objectives of covariate model development are really focused on explaining, understanding, and making inferences about the data. So first we want to explain the random variability in parameters in response, and I have random in quotes there because the variability we've observed in a population, be it on a PK parameter or an outcome measure, that's comprised of measurable sources but also random sources. And if we can explain the apparent randomness with something that's measurable, now we've learned something, whether it's causative or just correlated is another question, but at least we have some grasp on the understanding of that variability in the population. And the reason we want to understand that, of course, is to better use the drug in a clinical therapeutic use, better dosing rules, dosing adjustment in special populations, drug labeling, in a more scientific sense to allow for better control in clinical trials, setting inclusion criteria perhaps. In other words, to make inferences about the effects from the modeling results. Another goal is to improve the predictive performance of the model. So by adding the effects of covariates as part of the fixed effect model, we'll make better predictions for subjects in the current data set, maybe for simulations of future studies, and even for future patient populations. And I'm going to bring up the example we used earlier on to discuss the mixed effects model hierarchy. Remember when we were looking at the relationship between drug clearance on the y-axis and creatinine clearance on the x-axis, we noted that this system was characterized by considerable variability in drug clearance, but that a portion of that was explained by individuals' renal function as measured by creatinine clearance. And so that's a covariate that explains some of the variability. It doesn't describe everything, and there are still some unexplained reasons for some of these individuals to differ from the population typical expected value. But overall, we do have some predictive ability by incorporating the creatinine clearance as a predictor of clearance. Or in other words, we can make inferences about the creatinine clearance. For example, individuals with low creatinine clearance have lower drug clearance. And that could be useful for drug labeling, could be useful for dosing adjustment, and so on. So that's what we're after here. Well, we saw in that example a very simple linear relationship between individual clearance and the covariate creatinine clearance. But there's more than one way to implement these covariate parameter relationships, and I'm going to show you some of the commonly used ones, and I'll comment on their pros and cons and why you might use one over another. So let's start with covariate data that is it's measured on a continuous scale, so continuous data. Things like weight, creatinine clearance, height, they're all measured on a continuous scale. We can start with a very common expression here called the linear additive relationship, where we have the typical value of clearance in the population is equal to some relationship here. It's a linear model with an intercept theta1 and a slope theta2 times weight. This assumes a linear relationship between clearance and weight, at least through the range of the data being studied. Just because you pose a particular relationship here doesn't necessarily mean that it's going to be valid across the entire physiologic range, but it might be useful within the range of the data that you've observed. And then we just have simple individual clearance here, which is described by the typical value, which is individualized by the individual weights, but also includes now an exponentiated inter-individual random effect, the eta. So we can explain some of the variability with weight, but there's a remaining random variability that we're explaining with the eta. That's a linear additive model. It has some drawbacks in that it's difficult to interpret what theta1 means here. I guess at a weight equal to 0, your clearance should be equal to 0, but it's clearly just an empirical relationship for a segment of the parameter covariate relationship. Now the linear centered model is one that's a little bit nicer to work with. It's quite similar, except that instead of modeling weight as the variable observed, we're looking at this centered on a reference value. So now we're looking at some typical weight minus a reference weight, and so in an adult population you might choose 70 kilograms, for example. So then you have weight minus 70 here. That allows us a little more stability because it sort of balances the weight range around a pivot point. It also makes interpretation of the parameters a little bit more straightforward, so that when weight for the individual is equal to the reference weight, this term becomes 0, which drops the effect, and so theta1 can be interpreted as the clearance for the individual with weight equal to the reference weight. So that has some advantages, and it basically allows a little bit more stable estimation of that slope and intercept term. It still is a linear shape, and of course if you had a large negative slope theta2 here, you could potentially shift this relationship such that the typical value of clearance would go negative, and we know that's not physiologically possible. The same holds true for the linear additive. So there are other ways to parameterize models. Another one that's useful is a power model. Here we have indicated that clearance increases as a function of weight, or changes as a function of weight, according to this power relationship with some base term theta1 and a power theta2. Now the nice thing about this is that in the power relationship you can constrain clearance to be positive as long as theta1 is constrained to be positive here. It doesn't matter what the value of theta2 will be, and that's a useful constraint. But interpretation of the parameters is a little more difficult. It does allow for a bit of curvature in the relationship, which could be useful for some covariate parameter relationships, although depending upon the value of theta2, this relationship could appear to be quite straight as well. A very useful way to look at this is normalizing that power model based on a reference covariate. So now we have the same sort of relationship, except instead of weight, we have weight divided by a reference point. So individual weight divided by 70, for example. And that quantity is raised to the power theta2. Now this one has a nice advantage from an interpretation point of view, similar to the linear centered, in that when weight for the individual is equal to the reference, now you have 1 for this term, and so theta1 becomes the clearance associated with the weight for the reference individual. Theta2 is a power again. It could be, you don't have to worry about this parameter being estimated to a negative term because the entire clearance would be constrained to be positive as long as theta1 has a lower bound of 0. So that's a very nice model. It allows for linear and slightly nonlinear relationships. It constrains the parameter to be positive, and it makes interpretation easy. Now, another way you might code this is by using a log transformed relationship. And this is particularly useful when you're interested in creating a model structure that is consistent with the assumptions about the parameter estimation distribution. So the parameter estimation error, we assume, follows a multivariate normal distribution, and that's what's displayed to us in NONMEM in the variance-covariance matrix of the estimates. Well, when we understand that, that's saying that the imprecision or the uncertainty in these theta terms is normally distributed, or multivariate normal. And so for that to be valid, then all of these other models would fail because, of course, if theta 1 is negative, our typical value of clearance is negative, and that's not realistic. However, if theta 1 in this parameterization is negative, that's okay because this expression is for the log of clearance, not for clearance. And so actually what we've got here is the log version of the power normalized model with a slight difference here in that the intercept is equal to theta 1 still, where theta 1 now is log of clearance and not clearance itself. And then to obtain the individual clearance, you just exponentiate that function. This is a particularly useful way to model this, and with the new estimation methods in NONMEM 7, talk about that later in the course, but this modeling parameterization is analogous to the mu methods that they use in NONMEM 7 to help constrain the parameter distributions. Otherwise, the covariate effect interpretation is the same as it would be with the power model here. We have a log normal interindividual random effect. We have a power relationship for the ratio of weight to the reference rate weight, and that power is theta 2. Okay. For categorical covariates, we have similar model structures, although there are some slight differences. Categorical covariates are those that take on a value of a category, a 0-1 variable, yes, yes, no, for example. And we're using smoking status here as a yes-no indicator of a patient's status with respect to smoking. Here you might look at this in another linear additive term. We have a typical value of clearance equal to theta 1 plus theta 2 times this categorical effect, where smoking is a 0-1 value. So theta 1 would be the estimate of clearance, or the typical estimate of clearance for non-smokers, and then theta 1 plus theta 2 would be the estimate for smokers. We could model that in a different way, one where that effect is proportional. So that now that we have this relationship, theta 2 is the proportional change in smokers versus non-smokers. This is going to be some fractional change. If your estimate is 0.2, if the estimate of theta 2 is 0.2, we would say that smokers have a 20% greater clearance than non-smokers. That's another way to describe this. Yet another way is to use a power model. I like this approach. We have a typical parameter theta 1 times theta 2, which represents the fraction or the ratio of smokers' effects to non-smokers. And smoking now is a power, a 0-1 value. Of course, if it's 0, anything to the 0 power is 1, and so we collapse down to a reference value of theta 1 for non-smokers. If smoking takes on a value of 1, then theta 2 represents the ratio of the smoking effect relative to the non-smoking effect. So, for example, theta 2 of 0.75 would indicate that smokers have a clearance that is 75% of your typical non-smoker. This is a nice parameterization because it's quite analogous to another thing that we use in pharmacokinetics, and that's bioequivalence criteria. We're looking at a relative ratio. And the other thing that can be useful here is that we can use the confidence intervals around theta 2 to make inferences that are similar to those we might for bioequivalence. So for example, if theta 2 lands somewhere between 80 to 125%, that would maybe indicate that the effect is minimal or negligible. We can also write the power model in a log transform space, similar to the continuous model, where now we're just using the rule of logs here, where it becomes the smoking factor times the log of theta 2. Interpretation of theta 2 is the same. Next, we might consider combining both continuous and categorical covariates in the same model. And if we use the power type model or the multiplicative type model, then they're all just multiplicative factors. So we have an intercept theta 1, we have a weight effect here, theta 2, which is in a power model, normalized by the reference weight. And then we have a categorical effect, theta 3, which is the smoking effect. This gives us an easy to interpret model. Again, theta 1 happens to be the typical value of clearance for an individual with the reference weight and the reference smoking status here, or smoking status of 0. And so it makes that interpretation easy. It also constrains the model to be positive. Theta 2 and theta 3 can be estimated while still maintaining a positive clearance. Theta 3, of course, is going to have to be constrained at a bound of 0, as well as theta 1. And so it gives us some nice flexibility. Okay. Another issue with respect to covariate model parameterizations is that the relationship should be meaningful and should at least be accurate. So we want to look at how well does it describe the range of the observed data. And you could look at diagnostic plots across the range of the covariate, for example. Is the model constrained to plausible value? So can you easily constrain clearance to be positive? Is there some physiologically relevant relationship that could be used? Maybe something that's either theoretically or empirically derived ahead of time. And is it clinically relevant and useful? Are there relationships that have been defined in clinical applications that could be used to describe the covariate parameter relationship? The allometric model is an example of a physiologically relevant parameterization. And here's one where we have a weight effect built into clearance with an allometric exponent of 0.75 versus for volume and distribution, that exponent has been shown to be a value of about 1.0. And so in some cases you may decide to use that relationship a priori as the deterministic clearance body weight effect. Okay, before I move to the next topic, I'm going to review questions. Yeah, this is a good question. In fact, I forgot to mention this. So Francois asks, the power model for categorical covariates looks easy to implement or natural for a binary covariate like smoking. But what if you used an ordinal data, age categories or New York Heart Association scale, where we have values of 0, 1, 2, 3, and so on? So in that case, let me scroll back here. The categorical relationship has to be represented in such a way that we map the ordinal variable to multiple binary variables. So if you had 3 categories, let's say you had 3 different race categories, and you wanted to analyze those, you could just specify them instead of a single variable race, you might categorize it as race 1, race 2, race 3, and for each one of those, assign a 0, 1 value. Or another example, we have a treatment assignment, maybe a ConMed treatment assignment, treatment 1, treatment 2, treatment 3. Instead of coding that as a single variable, we could remap that into 3 variables that were each a 0, 1 binary variable, where the value of 1 would be used when that category is relevant, and all the others would be set to 0. So it still is a flexible relationship here. You just might have to remap your ordered categorical variables. Is a power model always preferred to the linear, additive, or the centered? There are lots of cases where the power models are preferred. They are more stable, for one, and they give you the flexibility of having relationships that are approximately linear, as well as others that can be quite nonlinear. And they also give you a stable parameterization and keep the parameter constrained to a positive value. So for PK parameters like clearance, I do like the power model, and I would probably use that as a starting point. Okay, just a moment here, see if there are any more questions. Okay, we'll move to the next topic. And this next topic is called data reduction before you start covariate modeling. So what do you think about before you start covariate model building? And this is an evolving science. Our work in population PK it keeps changing over time, and the way that we analyzed these models 15 years ago is different than the way we do it today. That's because we're learning as we move forward. We're also borrowing from other fields. And so this is an area where I've borrowed from another field in statistics, and with regression across multiple variables, where there's a useful strategy known as data reduction. So data reduction step is one where we want to look at the data, identify the range, and think about things before you start building a covariate model. So the first step is to examine the data, identifying the range and distribution of continuous covariates. What do we have coverage for? Are we going to estimate the effects of renal function if our lowest calculated creatinine clearance is 85 mils per minute? Of course not. So remember, just because you have a variable doesn't mean you're going to make a useful clinical inference about that variable. Do we have adequate representation of different categories in a categorical covariate? Very important consideration is whether or not we have strong correlations or collinearity between covariates. This is quite problematic in regression models, especially when we are trying to understand or make inferences. And so we want to select covariates with unique information. That might require you to create a composite or interaction effect to convert multiple correlated variables to a single variable. But there are different strategies, and we'll discuss that in a minute. Was the study designed to estimate covariate effects? Do you have an adequate support here? Most of the time, we haven't designed our studies to estimate covariate effects, so we've got to be careful about the power and the information content in the data. How do inclusion criteria impact the choice of covariates? Have you excluded everybody with poor renal function, for example? Does the covariate make sense given prior knowledge? Is it something that is consistent with your understanding of the science behind this particular drug? And which covariates are of interest from a clinical perspective? What are the disease states? What are the patient characteristics for which this drug will be used, and how do they impact the PK? You can propose some of these questions quite easily ahead of time if you understand the patient population. So let's investigate a couple of these data reduction tasks. One of them that's very important is the correlation collinearity issue. And here you see a scatter plot matrix of a covariate data set. The way to read these, if you recall, is that each variable here is plotted along the labeled axis. So this plot here is a plot of height on the y-axis versus age on the x-axis. This one here with a strong correlation is a plot of ideal body weight on the y-axis versus height on the x-axis. And then we have the complementary matrix here representing the correlation coefficient. So this is a useful plot to make for the continuous covariates. We want to make sure that we're bringing covariates to the model that carry unique information. And so things like height and ideal body weight we would not include as predictors of the same parameter in the same model. It would be confounded due to the correlation. However, other effects, maybe like the relationship here between ALT and creatinine clearance, we might be able to deal with that one. What should happen here is that when we build covariate models, the information that each covariate we add should be unique. In that, if you happen to remove that covariate effect, the rest of the model parameters are unchanged. And so a rule of thumb that I would use here is that when the correlation coefficient is absolute value of that correlation coefficient is greater than 0.3, think twice about using that predictor, those two predictors, at the same time on the same model parameter. This is consistent with some work also that was published a few years ago by Pete Bonnet looking at correlation of covariates, and he found a similar conclusion that this correlation should land somewhere. If the correlation lands somewhere between 0.25 and 0.5, then it begins to become problematic. So that's something easy we can do for continuous covariates. We can also check for independence between continuous and categorical covariates. Here we have a box and whisker plot of weight by male and female sex, and you see here that there's an obvious relationship that females have a lower weight than males, a lower ideal body weight, but body mass index and age are quite similar. And so you might then, if you're anticipating estimating a weight effect, you might avoid adding the effect of male or female sex to that model because there is a correlation here. And you can explore this graphically. You can also apply other tests, ANOVAs or Kruskal-Wallis tests, to look for significant correlation between categorical and continuous variables. Graphics are probably good enough, and again, you'd want to avoid those that have obvious relationships. Now, it doesn't mean that you have to completely avoid those from the analysis. It just means not to include them simultaneously as predictors of the same structural model parameter. So more solutions to the collinearity correlation question. Avoid simultaneous inclusion of suspect covariates. Another thing you do is remove the correlation. For example, the MDRD calculation for renal function is normalized by body surface area. So you can include that simultaneously with measures of body size. Whereas the Cockcroft-Gault calculation of creatinine clearance is directly influenced by body weight and is highly correlated with body weight. And so it's very difficult to estimate renal function as measured by creatinine clearance and weight effects at the same time, unless you normalize out that weight effect. Another possibility is to seek additional data where the same variables are independent. So, for example, if you're interested in the renal impairment, maybe study renal impairment to severe levels where now the relationship between creatinine clearance and weight are not correlated. And so that would add strength to your estimation of those effects. You could create a single summary variable to represent correlated predictors. Body mass index, for example, reflects both height and weight effects. So you could create a summary. It could be a standard measure like BMI, or it could be just some user-defined combination of those covariate effects. Another possibility is you could fix one of the covariate parameter relationships. For example, in pediatric PK analyses, age and weight are highly correlated because of the dramatic increase in body size as age increases. So it makes it very difficult to estimate effects that are age dependent from those that are body size dependent. However, if you fix the weight effect, maybe to some known physiologic relationship such as an allometric expression, that allows you to estimate the remaining age-related effects. And then finally, you might want to reserve the correlated covariates for secondary goals. Eliminate them from your first pass here for those effects that you really want to make inferences about. But you might include them later on as an exploratory modeling objective. So this is all part of the data reduction step. It's something that really should be considered at the time of writing the analysis plan, but certainly before you start to build the models. At least that's my bias on this. And I think it will lead to more meaningful covariate models and less confusing interpretation, fewer false positive relationships, and other spurious type results. Okay, any questions on data reduction? Looks like we have one here. Assuming we have a lipophilic compound, how could I test the effect of sex and weight on clearance, knowing that weight will be different between males and females, and that both sex and weight may be clinically relevant? Well, that's a good question. So you could look maybe for other measures, that other causative relationships here, such that might explain that apparent effect. For example, different indicators of body size. Maybe don't use total body weight. Maybe use lean body mass. Maybe use body mass index. And by using a different measure of weight, you might incorporate the real causative relationship in the difference between sex and between the sexes and clearance. That's one way to look at this. The other way would be to make some assumption about the weight effect, fix it. Assume that that's an allometric relationship, and you're just going to fix body size, and then estimate the remaining adjustment necessary to make males different from females. But if you put both of those in the model at the same time and try to estimate them, they're not uniquely identifiable anymore, and the coefficients for those covariates will not be interpretable in a univariate way. The other possibility is to create a composite, some sort of a sex weight composite there, where you may have. Well, that's a difficult one to do. I'm going to scratch that last suggestion and go back to using a different measure of body size that might explain the difference. Now, one thing you could do is you could remove or exclude, let's say we exclude sex as a covariate and we just build the model with weight. And then afterwards, having that fixed model for weight, look at the remaining differences between males and females. Whether you look at the random effects or you just, in addition to that fixed weight effect, estimate the effect of sex. And that could be a useful relationship. But, it's a difficult one to answer because when you don't have unique predictors and you don't have explanatory variables for why there's that correlation, it's really a confounded estimation problem. Okay. Any other questions on data reduction? Let's move to the next topic, which is the covariate modeling methods themselves. So I'm going to start off here with giving you basically the full story, where we started, and some of the things that we've used in the past in population PK, but also carry it all the way forward to more modern, more what I think are more relevant approaches. But I want to give you the full history. So first of all, initially there were some classic papers published describing some of these screening methods, or how we can use individual specific random effects to identify covariates that should enter the model. And this is a exploratory data analysis technique, or a data mining type technique, where you're looking at results of a model derived from a data set to identify which components of the data set should be included in the model. So it's completely data driven, and the model is actually confounded with that data set. But this is where we would use maybe exploratory graphical relationships between individual random effects, the individual etas, and covariates, and I'll show you an example of that. In addition to graphics, there were even proposed some statistical methods where you could run a screening technique to identify predictor covariates in a large data set. And initially these were done in such a way that there was no data reduction. Just every variable in your data set was regressed here using a generalized additive model or some other multiple regression technique versus the individual's random effects. And it was a stepwise regression. A quick way to screen covariates, you could identify signals this way, but really not a reliable way to do it. It focused, first of all, on the individual parameter outside of the PK/PD model context. So it didn't account for correlation of a covariate or potential impact of a covariate on multiple PK parameters. It didn't account for time-varying covariates as well. So if you had covariate of interest that changed over a long study, that was difficult to implement in these GAM-type models. Or imbalanced data. Again, it was treating all of these relationships as if they had arisen. It was basically a naive pooled analysis with respect to the individual random effects versus covariates. And of course, the results were dependent upon the precision and accuracy of the individual etas. More on that later. And there are a few packages that would implement this in an automated way. A key point here is that both the exploratory graphics and the GAM, which are what we call eta-based diagnostics, or diagnostics based on the individual random effects, they can be misleading in the presence of the eta shrinkage that we spoke about earlier on. Eta shrinkage is the case where the individual estimates are shrunken towards the mean estimate of 0, thus distorting the true relationship. But if eta shrinkage is not large, which you never know for sure, but if your estimate of eta shrinkage is small, you might use this to guide your covariate parameter relationships. And I would suggest that you don't use this to determine which covariates should be included, but you use it to identify relationships in the data, shapes of the relationships, and maybe what sort of structure might be used. However, other camps would advocate this as the way to define which covariates should enter into your covariate model. So here's an example of looking at an eta for clearance and an eta for volume, the left column and the right column respectively. And we're viewing it versus sex, versus weight, and versus creatinine clearance. I'm sorry about that. And then we have a third one here. We're looking at eta 1 for clearance versus age. And then eta 2 for volume versus weight. So this allows us to explore relationships. You see that there's a trend here between males and females. There's also a trend with respect to weight. So it could be that the weight effect explains that. We see with creatinine clearance a relationship in this particular plot that appears to be increasing up to a certain point and then sort of plateaus. So it might be a nonlinear type relationship, or maybe a segmented relationship. And with creatinine clearance, that's notorious because of the bias in the Cockcroft calculation when creatinine clearances or when renal functions are healthy. But that's the kind of relationship you might see as well. So that might change your strategy for the way that you would parameterize the covariate model. You can use ETAs, or you can use something called individual residuals, which is just simply the individual parameter estimate minus the typical parameter estimate, and explore these relationships. Okay, but be careful with these. I think it's okay to use these as a guide for the shape of the relationship. I wouldn't use them as a criterion to rule in or rule out covariate effects, although that has been done in the past. So those are two screening methods outside of the population PK model. There are also screening methods that incorporate the screening within the context of the entire PK model. So for example, building the covariate model and doing the screening within NONMEM. And approaches used typically for that are stepwise methods, stepwise forward, stepwise backward, and combination of the two. Let's take a look at each of these. I'll explain what they are, and then we'll talk about some of the liabilities associated with them, but also some of the potential benefits too. Stepwise forward addition. This is one where you're building a population covariate model starting at a stable base model with no covariates. Now, if you're going to do this method, please do the data reduction step first. If you don't do the data reduction step, these results are going to be uninterpretable in most cases. Even if you do the data reduction, there are some problems with interpretation. But in any case, it's not always done this way, but in this class, I'm going to suggest that you do the data reduction step first. But the stepwise forward is one where you take your candidate covariates, hopefully after data reduction, and insert them one step at a time using the likelihood ratio test. Essentially what you do is you add a covariate to the model, maybe the predictor of weight as a function of clearance, and you run that model, and you look at the objective function change according to the likelihood ratio test statistic, and for 1 degree of freedom here, you've just added one parameter, determine whether or not it's a significant effect, and then you rank those effects. You do this over and over again. Each effect, one at a time, called a univariate building, until you've identified the most important effect. And so that might be, weight as a predictor of volume, and you add that to the model. And now you do the next step, the next round does the same thing again, but now your base model includes that new covariate effect of weight on volume. And you step through again, and you keep building forward until there are no significant covariates left, where significant is defined by the likelihood ratio test. And so that's how you build forward. And it suffers a bit here because you have the lack of interaction between combinations of covariates. You're always starting with an empty model going forward. So one compromise or one improvement on that is to use a backward elimination. We start with a full model and remove covariates one at a time in a stepwise manner. So what's the full model? Again, in order to do this, you must do the data reduction step, and you'd specify a full model based on the range of covariates that you're interested in. Now, you'll see in the next step that sometimes you determine the full model based on a preliminary forward step, but I'll hold that thought for a moment. So starting at a full model here, for example, we have clearance, which equals some relationship of weight and age, and volume, which has some relationship with weight. You start that and you remove covariates one at a time in a stepwise manner. The way you do that is you set each effect to its null value. In this case, it's additive, and so it's going to be 0. But if it was a power model for a categorical covariate, the null value is actually 1. So you have to, think about the math here, what value of the theta causes that effect to disappear? And depending upon the parameterization, it could be 1 or 0, or, depending upon how you write the model, it could be a different value too. And so you do this one at a time. So it's still univariate deletion now, and do this until you've identified the covariate that has the least impact, the smallest impact on the objective function, and is not significant. And you remove that effect. Then that's your next step, reduced model. You do that again for the next round. Univariate deletion, remove the one that has the smallest impact, that is not significant, and you continue on. And typically when we do this, we're using the likelihood ratio test, but we adjust here a bit the p-value, so because of the multiple comparisons being made. It still could be difficult to determine if that's an adequate adjustment. It's certainly not equivalent to a Bonferroni, which would adjust for dividing that critical value by the number of comparisons being made. But it is an adjustment here. And so if you recall, the likelihood ratio test, significant change in the objective function for 1 degree of freedom is 3.84 units. And that's for an alpha of 0.05. If we adjust that to 0.001, that requires a critical change of 10.88 units. So you might do it that way if you're doing multiple comparisons. And then you keep reducing until you get to a final model. But I'm going to suggest a couple of questions here that we'll get back to later. What happens when a covariate effect is statistically significant but not clinically important? And that's a factor that's a conundrum that faces most analysts here doing this sort of work. And what about that covariate effect that's not statistically significant? Does that also mean that there's no clinically important effect? And oftentimes that's the interpretation, but as you'll see, that's not the correct interpretation. Forward and backward stepwise is a combination of these two methods. And so you get to that full model by stepwise univariate forward selection, usually at a more inclusive p-value, something less stringent, allowing more effects to enter the model, followed by a stepwise backward. This can be automated, and has been. I think it's still there in the PSN software, as well as other tools, and it requires a large number of model runs. The problem, though, with this approach, well, there are multiple problems with stepwise regression, but particularly in the case where data reduction steps are not performed, it really leads to difficulty in the interpretation. So let's talk about some of those problems. And all of this information comes from the statistics literature, and so we can certainly learn from our colleagues in statistics who have been telling us for a long time that stepwise methods are not a good way to make inferences about effects. They can be useful ways to build predictive models when we have testing data sets and really when we're doing data mining, but when we want to make statements about different effects, they're problematic. That's because they're based on methods that were intended to be used for pre-specified hypotheses. P-values then become difficult to interpret, and they're also difficult to adjust appropriately for the multiple comparisons. The other problem that we run into is that the regression coefficients are typically overestimated, meaning the regression relationships, when we're deriving the selection of covariates based on the data, there's a higher chance of a false positive finding or selection bias, so that those effects that by random chance appear to be related will be selected. And in that case, their coefficient would be overestimated. The other problem is that the confidence intervals are falsely narrow. That's because the stepwise reduced models don't reflect the entire uncertainty over the estimation problem that was actually conducted. They're limited to just that one final model. and really there was a lot of degrees of freedom there, a lot of uncertainty used to be explained across that multi-step regression problem. There's also severe problems in the presence of collinearity, estimation bias, interpretation difficulties. We've discussed that already. The resulting models can be predictive of the current data set, but sometimes difficult to interpret or generalize. They might actually be an overfitting of the data. And really, to do these well, you have to have very large data sets with rigorous multiple model checking and model validation steps. In NONMEM, our likelihood approximations here are known to result in incorrect p-values, even when you know the underlying model. And simulation studies have demonstrated this time and time again. So that's another concern, is that is the likelihood ratio test actually performing the way we think it is? Reconciling the statistically significant effects with clinically important effects is a challenge. Again, lack of statistical significance does not necessarily indicate a lack of effect, and that's because these studies are not powered for analysis of covariate effects. We're just taking whatever we get in the data set and looking for relationships. And without that adequate power, the lack of a statistically significant effect could very well be due to just a lack of information in the data and not necessarily a lack of a true underlying relationship. And as I mentioned, even with large data sets, these methods fail, where there's rigorous testing and cross-validation. And typically in population PKPD, we don't have the luxury of a large enough data set or enough validation test sets to perform this. So we're sort of caught here with a bit of history that's been used to guide these methods, and they're practical, it appeared to be practical, but the more you use these methods, the more you find that the interpretation from stepwise methods can be misleading. So there are other methods that we might consider: the WAM algorithm, genetic algorithm, and full covariate models, and some of these are quite similar to stepwise regression. For example, the WAM algorithm, this stands for walled approximation method. This uses the walled approximation to the likelihood ratio test for ranking of covariate submodels. So it's essentially equivalent to a stepwise backward, a stepwise backward approach, but it requires that you start off with a successful full model and get a variance covariance matrix of the estimates, a successful covariance step in NONMEM. By using that and the analytical approximation used in the walled approximation method, you can rank the 10 best models or 10 or 15 best models that are subsets of the full model with respect to this likelihood ratio test. And so then just run those 10 or 15 models rather than the full stepwise approach to confirm which one is the best predictor of the current data set. So this is an efficient way to do stepwise backward. It mandates that you carefully perform the data reduction step, avoid the collinearity, and all of those cautions we discussed in building a full model. But it is an efficient way to get to a reduced model for prediction purposes. Not necessarily for inference purposes, but for prediction purposes. The genetic algorithm has been proposed primarily by Mark Sale, where this is a complex algorithm where model components are viewed as genetic traits, and this is an optimization algorithm used in other fields, but applied to POP-PK models now, using different traits of the model characteristics as favorable survival characteristics. You can tune this to optimize, essentially automate a model selection process. Again, going into this though, there has to be some thought about what are the reasonable traits of this model, what are reasonable covariates to be entered, and there's essentially some sort of a data reduction step that's required here as well. It's a very computationally intensive method, but it is a completely independent machine learning method once you set up the initial parameters, constraints, and conditions. And then an approach that we've been using more recently and others is the full covariate model. And this is one that I find to be quite useful when your objective is to make inferences about the covariate effects. And for this approach, again, it's all within NONMEM or the population PK model. You define a stable base model structure based on goodness of fit. You do the data reduction step. It's not a data mining process. You don't search across all possible covariates. You focus in on those things that you want to make assessments on. And so it requires a rational selection of potential covariates for the full model, similar to the WAM algorithm or well-executed stepwise backwards. You reparameterize as necessary to develop a stable full model. This is important to have a model that converges. So you make sure you're hitting the global minimum, restart from different initial estimates, and so on. All the things that we've talked about. And then what we want to do is estimate all the parameters of the full model and construct some sort of interval around the estimate or posterior distribution if you're doing Bayesian estimation. Bootstrapping is another way to get at this, where we want to describe not only the parameter point estimate, but some interval about that parameter. And we make the inferences about the covariate effects based on that interval or posterior distribution. Exploring remaining trends then is secondary hypothesis generating work. So how do we decide what to include in a full model? And this applies to the full covariate model approach, to the WAM, to a stepwise backward from a full model, and even some of these ideas apply to the initial setup of a genetic algorithm. We talked about data reduction, so that's the first piece. Then create focused questions about specific covariate effects based on scientific or clinical interest. What is it that you want to make a statement about? What is it that you want to see in the drug label for this patient population? Base the covariate effects on mechanistic plausibility, prior knowledge about existing relationships. All of these things can be defined ahead of time with a bit of knowledge about the patient population that you're entering and the particular mechanism of drug action. You should be able to specify those covariate effects for which you're interested in obtaining some inference. Then exploratory graphics can be used to view the shape of the relationship to help you identify the parameterization. Again, avoiding simultaneous inclusion of correlated predictors and making sure that you have an adequate design or range of the covariate of interest. So if organ impairment was an exclusion criteria, don't worry about including that in your model. And then usually you write a pre-specified plan, and you can create a table something like this one, where we'll identify the model parameters and the covariates that we want to investigate. So weight we'll look at as a predictor of all of these parameters: clearance, V1, Q, and V2. And why? Well, because we're interested in the weight effect. Age we might just consider for clearance, because that's really what's going to be driving our dosing determination here for a chronically administered drug. We might look at things like disease state, liver function, Child-Pugh score as a predictor of clearance, because we're interested. We know that we might be administering this drug in a hepatically impaired population, and so we'd want to be able to characterize the impact of hepatic impairment. We also maybe know that the liver is involved here. There's hepatic metabolism involved. It's a CYP3A4 substrate. Drug interaction, we might be interested in a known 3A4 inhibitor, which might be a conmed. So these are the kinds of things with a little bit of clinical pharmacology knowledge that you should be able to specify ahead of time. And if you're not sure if you're interested in something, but you think it might be clinically important, then include it. Add it to the full model. This doesn't mean, just because you're pre-specifying covariates, it doesn't mean that you have prior knowledge that all of these are clinically important predictors. It's just an indicator that they are clinically interesting, and you want to understand the relationship. There's some hypothesis that you want to address, or maybe there's some labeling information that you want to be able to provide with respect to this particular covariate set. Then after you've done that, parameterize the model in a stable way. Here I have an expression defining the relationship for a full model using a power normalized relationship for continuous covariates. That's this first section here. And a power model for categorical covariates here, where you have a value of theta raised to a 0,1 flag for the categorical covariate. And we simply have a baseline parameter here, theta n, which is the typical estimate at the reference covariates. And depending on how many of these continuous covariates, you just take the product of all of these times the product of all of these categorical effects. And that's how you string them together. This becomes a very stable model because it's easy to constrain the parameter to remain positive, which is important in PK models. It's also stable estimation because you're centering the covariate effect. And it's also easy to interpret because the power effect is something that we're used to seeing. And also the categorical covariates are analogous to a bioequivalence type inference about the covariate effect. So this is one suggestion. I find it quite useful. Or another useful way is the log transformed version of this relationship. So let's look at the results from some of these. Here are some examples. These are from published population PK analyses or PD analyses. This one is the effect of covariate effects on varenicline pharmacokinetics. And what we've got here is a relationship of various covariate effects with respect to clearance, volume of the central compartment, volume of the peripheral compartment, and intercompartmental clearance. The scale on the bottom here is the change relative to the reference individual. So the reference individual is pinned here at 1, and that's what this vertical line indicates. That's a reference individual. There's a plus or minus 25% box around that, just for a reference. And then we have the covariate relationships plotted. So for example, what's the impact of renal function? Well, creatinine clearance here is explored. And in this case, weight was not estimated as a predictor. Creatinine clearance was used instead of weight. And there's a box and whisker plot showing the range across the range of creatinine clearance, but it's probably more informative to look at the individual cuts of creatinine clearance at 20 mils per minute, 40 mils per minute, 65, and so on. You see here the point estimate and the confidence interval, or the bootstrapped credible interval here, which describes the uncertainty in that effect. And you see that at low creatinine clearance that there's a considerable difference between these individuals compared to the typical individual. Probably about a 40% reduction here in clearance, which would correspond to an increase in exposure. Whereas when we look at race effects, black or other, it looks like those effects are quite small. They're precisely estimated, but they're still quite small, less than a 25% change here. So on their own might be considered to be clinically unimportant. Similarly, when we look at weight, we see weight effect on volume. That's expected. The age effect on volume distribution is quite poorly estimated, and you see by the large whiskers here indicating poor precision around that. Although it extends into regions that might be considered clinically important, it's very difficult to rule out this effect. In a p-value driven approach, you would probably say that this is not statistically significant because it covers a it covers the null value here, or equal to the a value that's equal to the reference individual. But the imprecision here indicates to me that there's not enough information to make a conclusion about that effect. Then we have a race effect here again, small, poor, well estimated, actually intersects the null value. But then this other effect on race, well, that one's not so well estimated, and its point estimate pulls you a little bit further away. So this might be a bit more interesting from a clinical point of view, something that you might have to pay attention to. So that's one way to view the results. Here's another way, completely analogous. This is for a pharmacodynamic model where we're looking at the effects of covariates on the probability of quitting smoking in a week 9 to 12 interval here. And so the vertical line at 1 is your reference individual, and you see that different effects are shown for different covariates and the precision around those effects. So females are not quite different than males here. The point estimate's right on the null value, and the imprecision or uncertainty is quite narrow. Whereas, those individuals who take their first cigarette in the morning, greater than 60 minutes after waking up, well, they have a higher quit probability than your typical individual. Those that take it more earlier in the morning probably have a lower probability of quitting. There's maybe a higher level of nicotine addiction there. Age effect here shows the relationship between 18-year-olds and 75-year-olds, where the younger individuals are probably less likely to quit, whereas older individuals might be more motivated. But there's good information at the higher end, but poor precision at the lower end, probably because of the data. Race effects here, you see that there's one effect that appears to be statistically significant in that it doesn't overlap the null value, but the effect is probably quite small, but relatively imprecise. Okay, so that's how we can look at these. Now, another thing we want to do after looking at these relationships is to make sure there's nothing remaining. So we could plot the conditional weighted residuals or the ETAs from the full model versus any covariates in the database. And these could be anything. This could be plotted versus covariates included in the full model, as well as those that were not. Remember, this is a checking step. It's a hypothesis generating step. It's not one that you would use to make inferences about the covariate effects. But what you'd like to see is that there's no remaining trends with the conditional weighted residuals versus categorical effects or continuous effects. The other thing you could do is you could take that full model, fix the parameters, and then proceed with a stepwise regression, maybe a stepwise forward, starting at the full model being fixed, with the caveat that this is purely a hypothesis generating exercise. These are covariate effects that you didn't really care about. They just happened to be in your data set. But if you wanted to look for a more data mining type exploration, you could do that stepwise approach from the full model. Talking about inferences again, when we go back to those plots, we could then maybe categorize effects as clinically important, not clinically important, or that the information is insufficient. If it's clinically important, that means that posterior distribution or that interval of the covariate effect would result in some effect. The entire interval is beyond a predefined clinically important change. So in the absence of knowing what that change is, we might define it as a bioequivalence criteria plus or minus 20% from the null value. And so we might say something's clinically important if the entire interval was outside of that null value. You might say something's not clinically important if the entire interval is within the plus or minus 20% null value. Now, that doesn't mean that it's not important in combination with other effects, and you could explore combinations of effects and their importance. But as an individual effect, it probably indicates that on its own, you don't have to worry about that covariate. And then lots of times we end up in this category of insufficient information. That's where the posterior distribution or the interval is broad and spans across a value of the covariate effects that both might be considered clinically important, and then another part of the range might be non-important from a clinical point of view. And that's because we don't have sufficient data or estimation precision to determine that. When you look at these three categories, the first one is one that would be statistically significant in most cases. In fact, if it's clinically important, it would always be statistically significant. You could run into a case where you have something that's statistically significant but not clinically important. But then the effects that are not statistically significant, they could be categorized in either two of these. Either there really is no effect or that there's just insufficient information. And that's a useful thing that only the full model can help you to understand. In addition to those categories, we could just be descriptive about the effects, where we describe the probability of being clinically important using the posterior distribution, the reference range, link it to exposure response potentially, look at the impact on derived parameters such as AUC and Cmax. These are all possibilities. And here's an example of doing that, where we're looking now at effects of covariates on clearance relative to the reference individual. And we have a plus or minus 25% range defined here for some reason. But now we're quantifying the effects. So, for example, the second value here is the effective 50 kilogram weight on clearance. Well, the number indicated here, 23 to the left and 77 to the right, that indicates that there's a 23% chance that that somebody with a weight of 50 kilograms has an impact on clearance that we would consider clinically important if this is our boundary. Whereas there's a 77% chance that it's not clinically important. When we look at other effects like this one here, all of the age effects, well, they're completely contained within this null value. There's a 71% chance that it's lower than the reference individual, or 29% chance that it's greater than the reference individual in this case, but 100% chance that it's within this not important range. Whereas somebody with a weight of 125 kilograms has about 100% chance that that their effect is going to be clinically different from the typical reference range. So again, we could pose these cut points that you're going to make a decision at, and quantify the probability of being beyond that range. That's a useful descriptive way, and sometimes is a useful way to represent the results to development teams or those that need to make inferences about the effects. You can take the full model a step further by reducing the model for predictive purposes, where you would drop covariate effects that meet both these criteria, not statistically significant, in other words, the confidence interval includes the null value, and not clinically important. The entire confidence interval is contained within the no effect range. If you meet both of those, I think it's safe to remove those from the model. But you would retain everything else because there's utility in maintaining those covariate effects. One, if they're clinically important, you want to include them. If they're statistically significant, so there's enough power there to differentiate them from the null, you probably want to include them to refine the estimate in future studies. And if they're not statistically significant but might be clinically important, so there's that insufficient information, the poor precision, you can't rule out the effect. And so you'd want to also include that in your model moving forward, because you'd hope that as you go to the next study or getting more patient experience, that the precision of that relationship would be improved, and then you could determine whether or not it's clinically important. The other thing too, the other check is that removal of any covariate effect from the full model should not So removal of any one effect should not impact the coefficients for the remaining effects. And that's a test of the independence of the information carried by the covariates. So this results in point and interval estimates that can be used to assess clinical relevance and how precisely the parameters are estimated. They're also resulting in a more accurate reflection of estimation precision. Remember, I mentioned that stepwise approaches result in falsely narrow confidence intervals. Full models result in the appropriate confidence intervals. Covariate selection here is not subject to problems of eta shrinkage. We're not basing the selection on eta diagnostics. And it allows us to understand why some effects have no impact. Is it because there's no effect, or there's not enough information in the data set to estimate that? And we can remove the models if necessary and move forward with a reduced model. So that's the full model. There are a few other statistical considerations. I'm going to take a glance at the questions that came up during the covariate methods and see if we can answer a few of those. Okay, so if following the full model, you see a covariate effect not previously tested being significant. So I'm assuming that you're doing some additional exploratory testing there. So you've pre-specified a full model, and then you might fix that model and do an additional stepwise, and you see something significant. Okay. Significant based on a likelihood ratio test. Well, if that's the case, in my mind, that's a signal in a data mining type exercise. It's a signal that may or may not be something that is of concern. But it is a signal that could be evaluated. It's a hypothesis generating exercise. It's not something that should be used to base labeling on or to base dose adjustment for a future study. Because remember, it's completely data driven. So it could be subject to selection bias, overinflated coefficient, all of those problems. What I would do is maybe consider that covariate effect, and if it's not correlated with anything else that's already in the model, maybe look to study that in a future study. But if it's just a signal that there is something that you didn't really care about to begin with, so maybe it's not even relevant. Maybe a parameter like a covariate like shoe size, for example. You may be significant, but it may not be something that you really care about. So again, use that one with caution. I would treat it as a hypothesis generating finding, not as something that you would use to make a formal inference or or even for drug labeling. The next question, explain further how to differentiate between no effect versus not enough information. Sure, let me show you. We'll go back to a graphic. Let's pick something like this plot here. So we could say here that for example, black race effect on volume and distribution here. The point estimate is close to the null value, and it's within what we've called our no effect range here, plus or minus 25%. And that's just set arbitrarily based on bioequivalence type criteria. It's probably conservative. It's probably true that if you had a 30% effect, it might not be clinically important, and that can only be viewed in terms of an exposure-response relationship. But taking a conservative approach here, plus or minus 25%, we'd say, okay, no effect here. And the reason we can say there's no effect is because the effect itself, the point estimate is within the null, as well as the interval. Okay, the interval here spans a region that's close to right on the reference value down to about 85% of that individual. So the precision on this is tight. It's clear that we've been able to estimate precisely the effect of black race being a very small effect, versus looking at this other effect here, race other. Race other, well, we haven't got the same precision here. There's probably not as many individuals in that category, so the precision is less precise, broader interval, where the point estimate lands outside, but there's a good proportion of this interval that lies within the region that's defined as not clinically important. So what happens here is we have an effect that spans both the potentially clinically important side and the not clinically important side. In that case, there's insufficient information to rule it out. We don't have a precise enough estimate. If we were able to add more data in this particular race category, you might see this interval shrink and see that, oh yeah, there's maybe a 60% effect here, or a 40% reduction relative to the individual. Or maybe that effect is closer to a 20% drop at 0.8. But as it stands, we don't have the power in this analysis to make that conclusion. Okay, so that's the differentiating factor. It's really, how precisely is the effect estimated relative to whatever boundaries you determine are going to be clinically important, or at least potentially. In fact, it's easier to determine boundaries that we say we're confident are not clinically important. Just because something is outside of that doesn't necessarily mean it's clinically important, but it would be something that you want to look at and then translate to response in one way or another, either through a PK/PD model that links exposure to efficacy or safety or something like that. Okay. Let's move on. Some statistical considerations, and I'm just going to highlight things that I've already alluded to. The parsimony principle. We'll start with that. Parsimony principle states that all things being equal, choose the simpler model. So you have to think about the purpose here. Because in order to determine that if all things are equal, you have to understand, well, equal for what? For what purpose? I would venture to say that if you use stepwise reduction, the models don't allow for inferences about the non-significant effects. So therefore, they're not equal to a full model. So for the purposes of making inferences about all the covariate effects that you want to make a statement about, the full model is the most parsimonious. That's as simple as you can get, while still being able to accomplish your goal of making inferences about the covariate effects. And if your purpose, on the other hand, was to make a prediction of concentrations in this data set, well, you might be able to use stepwise reduction to come to a model that predicts concentrations in this current data set at a more parsimonious way by reducing the covariate effects. But that model doesn't allow you to make the inferences about the covariate effects. And I just highlighted here that this is a common theme. It's been known under different famous quotes here. There's Occam's razor. Isaac Newton has a similar quote. Albert Einstein. All of these are different restatements of the same problem. But in each case here, there's the caveat that you need to make sure that you simplify, but not any simpler than you need to for the purpose at hand. Okay, so we'll get to this later when we talk about aligning the purpose with the method. But I just thought it was interesting to reconsider parsimony a little bit in the context of covariate model inference. Okay, likelihood ratio test. Remember, this is another concern and commonly used here in stepwise methods. Remember, it compares goodness of fit for nested models. There's this -2 times the difference in the log likelihoods is approximately chi-square distributed. Sorry, there's a typo here. It's chi-square distributed. And we can use that degrees of freedom to determine the critical p-value change. I'm sorry, the critical value for a particular p-value. And I illustrated this earlier in the course, where we show an effect on clearance, a smoking effect here. It drops the objective function to 483, but the reduced model without smoking has a minimum objective function of 490. That's a delta of 7, which is significant at 1 degree of freedom and p less than 0.05. But it's not if you're doing multiple comparisons and you adjust for that. But really what's more important is how big is that smoking effect? How well do we know it? So what's the point estimate? What's the interval for the difference between smokers and non-smokers? So be careful of the likelihood ratio test, and remember the approximations we use in the likelihood and be sensitive to assumptions, the normality of residuals, the assumptions about the likelihood simplifications that we make. Actual significance might be very different than the observed or apparent significance level. It's been shown that FOC interaction does a pretty good job of getting this right when the model is known. We don't know what happens when the model is misspecified, and that's not the case in all cases. So, if you really need a p-value, you might reconsider. What I would say is maybe use a likelihood ratio test as one of several model selection criteria, but not as a hypothesis testing tool. It might be more useful in helping you to select a structural model. Also consider things like AIC, diagnostic plots, minimization status, and so on. If you really need a p-value about a covariate effect, so and typically the only time we really need a p-value is if we're making some sort of a pivotal assessment, something that's a confirmatory analysis, and you probably would have powered the study to estimate this. You can use something called a randomization test, which will protect you from some of the problems in the likelihood approximation with NONMEM. And we'll talk about this in the model evaluation lecture, but it is quite an arduous and compute-intensive process. So you really have to think about when do you really need a p-value for a covariate effect. That's not how we will interpret the result anyway. So really making inferences based on effect estimates and the precision around those estimates is much more relevant. So let me close here by addressing this broader view that there are different methods that can be used, and they're valid in different cases, but it depends upon the purpose. So let me categorize them in different ways. If we're interested in generating hypotheses, doing data mining, we have no clue, we have maybe no idea of what our patient population will look like, maybe no idea of what is clinically interesting to us, and we want the data to drive everything. That's when stepwise methods can be useful. Again, those findings are better for hypothesis generating exercises than for formal conclusions or inferences. If you want to make inferences based on estimation of covariate effects, the full model is the best way to go. If you want to make predictions, well, you might choose different methods for different reasons. So stepwise methods are useful for prediction if you have a large enough data set, inadequate test data sets. But selection bias can still play a role here. If you do the data reduction step, then stepwise reduced models can be very efficient ways to predict the current data set and maybe future data sets. Full covariate models result in a larger reflection of the parameter uncertainty, but they can also lead to a larger prediction error of the response because of the inclusion of all of those effects. And so some of these small effects that are not well defined might lead to a larger prediction error. However, if you're going forward into a new situation where one of those covariates that was maybe classified as insufficient information, where that covariate is now better represented, you want to pull that covariate forward. You don't want to throw it away because you haven't made a conclusion about that effect yet. And so you can think of this modeling process here as not just one final analysis at the end of the game, but really as an evolution of a model throughout drug development, throughout clinical use, as you gain more information, as you expose the drug to more patients. And if you're going to do hypothesis testing, that definitely requires that you define the hypotheses up front, that you adequately power and design the study to test the hypothesis. Stepwise methods are not appropriate for this. What you could use is a limited full model that addresses the specific hypothesis that you want to test. Okay. I'll pause for a moment and answer questions. Looks like no new questions. Let me introduce then the practice problems. The first one is more of a thought exercise, and we'll discuss this on Friday. But I want you to think, what if you had a POP-PK data sets, pretty decent size, 300 subjects, 4 samples each. You have a simple model, one compartment with large variability, and in vitro that there's been identification of a potential drug-drug interaction, and it's a con-med that's commonly used in this patient population. So you want to confirm that effect in the current trial. You have other covariates to think about. These have been collected: weight, race, age, sex, liver function tests, creatinine clearance, and a couple of con-meds. And this is what you've got. These are data that have been collected. I want you to think about the steps that you would take to undertake the building of a covariate model, including some details: the plots you might create, the estimation methods you might use, the covariate model building method, how you might check some of the assumptions. Just think about that. And this will be more of a discussion point, but if you want to start this as a thread on the course site, we could collect our thoughts there and maybe discuss it on Friday. So this doesn't require you to do any hands-on modeling, but just some thinking about a problem and what points would you consider. The second problem, however, is a hands-on modeling problem, and this is a POP-PK data set with covariates. I've already created a data set for you. It's a multiple dosing data set, 10 doses, 900 milligrams, every 12 hours, administered by constant rate infusion. It's a 3-hour intermittent constant rate infusion. There's multiple samples along the way here, plus some troughs. I'm giving you some initial estimates for the one compartment disposition parameters. I want you to specify what the model building method should be, the goodness of fit criteria, which method you would use. Think about that. And then go ahead and do it. Build a covariate model. And there's a specific question here. It says define the impact of renal impairment on clearance for the drug label. And this is a little bit of a tricky question. I'm going to warn you about that. But if you follow some of the principles that we just discussed, you'll be okay. I've given you a data set. It's called POP-PK with coves.csv. It's on the course site. And the structure of this will follow very closely to what you've done in the past couple weeks on the individual and population PK models with the PrEP-PP library. In fact, if you use that last example as a template, you should do fine. We'll review that on Friday, and of course I'll try to answer questions throughout the week as well. But that's a covariate POP-PK data set that you can have a chance to play with, and we'll discuss a potential solution for that at the lab session. In addition, I've listed some references here of different topics in covariate model building, plus some study guide questions, which should be pretty easy to answer after listening to this lecture. But think about those. Again, these are hints of what might be included in the exams. Okay, that's the conclusion of our topic for today. I'll pause just for a few more minutes here before we wrap up to answer questions. It looks like no further questions, so we'll wrap up for today and pick it up again in the lab session this Friday. Thanks for your attention, and enjoy the rest of the week.